everyone, today I'm going to go through 22E, which is linear representations of nonlinear relations. What we want to be able to do today is to recognize nonlinear graphs of the form of y equals kx to the power of n, so of varying degrees. To be able to linearize nonlinear graphs by sketching y versus x to the power of n. So this is both when n is equal to 1, 2, 3, also -1, -2, and so on. So it's graphs that we've looked at before. We want to be able to find the rule of a linearized graph and to also be able to find the gradient of nonlinear graphs and use this to complete plots. So I'm going to start going through the first example in your summary book of 22E. So if we were to consider the relation of the rule y equals 2x squared, a linear graph can be obtained by sketching y against x squared. So what I'm going to do first is sketch the actual equation of y equals 2x squared, and then I'm going to show you what it looks like when we linearize it. If you think back to statistics, this is very similar to chapter 5 where we linearized data. So here are all of our x values. We're considering the x values between -2 and 4. And so for the rule of y equals 2x squared, what this will look like, firstly, x squared will be 4. Then that's going to be 1, 0, 1, 4, 9, 16. So all I've done is I've squared all of the values over here. And then y is 2x squared. So what do I have to do to get to there is simply multiply by 2. So that's going to become 8, 2, 0, 2, 8, 18, 32. So those are all of my values. Now if I were to sketch y versus x, so right now what I'm going to put on the graph is this is going to be my y-axis and this is going to be my x-axis. So for x, what I have is firstly -2, -1, 0, 1, 2, 3, 4. And for my y values, I'm going to go up by 2s. I know that that's probably not going to reach 32, but I'd rather have a zoomed in image of what it looks like rather than going inaccurately. So 2, 4, 6, 8. Okay, so now all I'm going to do is go ahead and plot all of these points on. So when x is -2, y is equal to 8. When x is -1, y is equal to 2. When x is 0, y is 0. When x is 1, y is 2. When x is 2, y is 8. When x is 3, y is 18. So you can see if I were to plot a line through this is not going to be a straight line. In fact, this is a parabola that will go through all of these values, and a 4 will be somewhere up there. Okay, it's obviously a non-linear graph. This is what we call a quadratic. In this case, we do have the equation. We know that it's y equals 2x squared, but if we weren't given the equation, it would be quite difficult for us to be able to tell what the equation of this very messy parabola is. Once again, just pretend that this is nice and neat. Okay, let's try and graph that a little bit differently. This time what we're going to do is we're going to graph y versus x squared. So this is going to have all of my y values here, and this is going to have all of my x squared values. And let's see what happens to our graph. So same idea with my y's, we're going to go up by 2's. I'm not going to be using the values of x, rather I'm going to be using the values of x squared. So I will go up by 2's for this one as well. And we haven't reached our final value, but you'll get the hang of it before we do. So let's plot these two values on. So I'm plotting x squared and y together. So when x squared is 4, y is 8. When x squared is 1, y is 2. When x squared is 0, y is 0. When x squared is 1, y is 2. We already have that coordinate. When x squared is 4, y is 8 once again. When x squared is 9, so 9 is over there, y is 18. And then when x squared is 16, y is 32, so we don't have any of those. Can you notice anything special about this? It is a straight line, so if I were to draw a line through that, once again pretending that is straight, we get a straight line here. Okay, so now what we've done is we've been able to linearize our relationship, and we know how to find the equation of a straight line. So if I know that this is the relationship between y and x squared, all I need to then do is find my m, and in this case we've just been calling m as k, and then of course our y-intercept as well, c. If we have a look, it passes through the point 0, 0, so my y-intercept is just 0, so that's going to be gone, that'll just be 0, and then to find k, all we have to do is find 2 points. There's 0, 0, and I can also use any other point. Maybe I'll use the point 1 and 2 to find my gradient. Let's give that a shot. So in this case, we're calling our gradient k, it's y2 minus y1, so that'll be 2 minus 0 over 1 minus 0, which will give me 2. And so y is going to be equal to 2x squared plus 0, which will give me y equals 2x squared. Now we already know this because that's the rule that they gave us, but if they didn't give us a rule and they only gave us numbers to plot on, this is how we would go about doing that. So hopefully now you understand the whole basis of this exercise, and we can now begin to apply it to other scenarios. So in general, if the graph passes through the origin, that means our y-intercept is going to be 0. So it's going to be of the form y equals kx to the power of n, and n can be 1, 2, 3, -1, -2, of whatever form it happens to be. Okay, and that's it. That's really the whole idea of this exercise. So let's try a couple more questions to get our head around that. A graph of y equals 1 over x is as shown below. The rule connecting y and x is. So the first thing that we can notice is that it is going through the origin. So once again, our c is simply equal to 0. So we know it's going to be of the form y equals kx to the power of n. N in this case is going to be -1, because what that will do is x to the power of -1 is the same as writing 1 on x. So all you really need to do is look at this variable over here, and that will tell you what this is going to be. So we're working with y is equal to k times 1 over x, and now all we want to do is find k. So we want to find the gradient of this graph. Here's k, we want y2 minus y1 over x2 minus x1. Find 2 coordinates, so we have one coordinate here, which is 0 and 0, and they've also given us another coordinate. So that's x2, y2, x1, y1 will be 0 and 0, so we can go 1000 minus 0 over 10 minus 0. So that'll be 1000 divided by 10. That will cancel out there, and that will be 100. So the gradient is 100, so that's y equals 100 times 1 on x, and all we need to do is multiply that to the top, so that's the same as saying 100 on x. And that is A. Okay, example 34 from your book. The following set of data is known to satisfy the relationship of the form y equals kx cubed. So over here what we have are our x values and our y values. If we were to plot x against y, what we expect to get, because it's an x cubed, is a cubic. So it'll look something, and it starts at 0, so it'll look something like this. Now we don't want a nonlinear graph, what we want is a linear graph. So what we need to do is not plot y against x as that one is. Instead what we need to do is plot y against x squared, x cubed, so we can get a straight line and find the gradient from there. So what we want to do here is find out, well, what are the values going to be if I were to write x cubed? So all I'm going to do is just cube all of my x values that are in this row. So 0 cubed is just 0. 2 cubed is 8. 3 cubed is 27. 6 cubed is 216. And 7 cubed is 343. So if I were to plot all of these values here against y, that's when I'll get my linear graph as shown over here. So our k is going to be y2 minus y1 over, in this case we're not working with x, we're working with x cubed, so it'll be like x cubed 2 minus x cubed 1. All we need to do is pick out 2 coordinates. So the easiest coordinate to work with is 0, 0, and then we could also work with, remember it's not x, we're working with x cubed, so that's 8 and 28. And so all we want to do then is label them. So this is going to be x cubed 1, y1. This will be x cubed 2, y2, and then just apply that into our formula. So that'll be 28 minus 0 over 8 minus 0, which will give us 3.5. So my k value in this case is 3.5. If I were to write the equation, that would be y is equal to 3.5x cubed. So the main thing to remember here is you must transform your data. You can't find the gradient of y against x because we know it's a nonlinear relationship. Instead, what we need to do is find it of x cubed because it is that nonlinear relationship, so first we have to linearize it. So to complete the table, all we now want to do is sub in our values of x into our equation of y equals 3.5. Instead of x cubed, what we're working with 6 right now, so that'll be 6 cubed. So that's 3.5 times 216, which will be 756, so that will be the value for that one. And then finally, to find the value for 7, we'll have x equals 7, y equals 3.57 cubed, which will be 1,200.5. And there you have it, that's how you complete your table. Your next example 35 is pretty much the exact same question. What I would like you to do is to do this by yourself, and then we will have a look through it in class. And that's it for this exercise. So to quickly revisit those learning intentions, today we've been able to recognize nonlinear graphs of the form y equals kx to the power of n. So we looked at x squared graphs, x cubed graphs. We even looked at a graph that's 1 over x. We want to be able to linearize nonlinear data by sketching the graph of y equals x to the power of n. And you saw that previously. We had a graph that looked curvy, and then when we graphed it with x to the power of n, it became a straight line. From there, we were able to find out what k equaled, and that allowed us to find the rule. So I should be tweaking these along the way. And then finally, we were able to find the gradient. So the gradient was k, which was our y2 minus y1 over xn 2 minus xn1. So I hope that's all helped, and we'll practice this a little bit more in class.